High in the mountains of Colorado, crews are raising a dam that was never meant to be raised this way. The engineering is advanced, the funding is secured, and construction is already underway. Yet years into a $500 million modernization, the system designed to deliver more water still cannot legally store a single additional drop. A concrete wall built in the middle of the 20th century is being asked to do something it was never required to do before. For decades, the Gross Dam functioned as designed. It captured runoff, regulated seasonal flows, and fed a growing metropolitan system without drawing much attention to itself. The reservoir behind it filled and emptied within predictable limits. The system worked. That balance no longer holds. Demand on Denver's water network has increased steadily, while the margin for error has narrowed. Drought cycles have lengthened. Wildfire risk has intensified. Flood events have become more erratic. The dam did not fail under these pressures, but it reached the edge of its original design envelope. The constraint was not the river feeding it, but the height of the structure holding the water back. Raising a dam is not a common operation. Most large dams are built once, filled once, and left structurally unchanged for their entire service life. Gross Dam is an exception. From the outset, its designers anticipated that future conditions might require additional storage. The foundation, geometry, and abutments were sized with that possibility in mind. The structure was not overbuilt, but it was not closed-ended either. What followed was an unusual decision. Instead of constructing a new dam elsewhere, Denver Water chose to expand the existing one vertically. The logic was straightforward. The reservoir already existed. The watershed was already tapped. Increasing the dam's height would increase storage capacity without introducing a new footprint into an already constrained river system. On paper, the math worked. Increasing the crest height would allow the reservoir to hold nearly 3 times as much water as before. In system terms, it would rebalance where water was stored within the regional network, shifting capacity northward and reducing reliance on reservoirs further south. The additional volume would act as a buffer against multi-year droughts and sudden runoff events. But the engineering challenge was not simply a matter of adding concrete. The original structure was a gravity dam, relying primarily on its mass to resist the force of the water behind it. The expansion required a different approach. As height increases, the forces acting on the structure change. Weight alone becomes inefficient. Instead, the raised section would function as an arch dam, transferring load laterally into the surrounding rock walls. The finished structure would behave as a hybrid system, with 2 different load paths working together. This transformation introduced complexity at every interface. Old concrete had to bond with new concrete. Thermal behavior during curing had to be tightly controlled. Differential movement between materials could not be allowed to accumulate over time. The dam could not behave like 2 structures stacked together. It had to function as one. Construction began with this objective in mind. The upstream face remained intact while the downstream side was stepped outward, creating a terraced profile that increased stability as height increased. Each lift added mass, but also redistributed force. The system was being reshaped incrementally, not replaced. From an engineering standpoint, the process was advancing as planned. The structure rose. The material performed within specification. By mid-decade, the expanded dam had reached the height of the original crest. Yet, despite visible progress, the system remained incomplete in a critical way. The physical structure was ahead of the institutional system governing it. The dam could now hold more water. The reservoir behind it, legally, could not. That disconnect would become the defining problem of the entire project. The Gross Dam was completed in the early post-war period, when Denver's water system was designed around predictable growth and relatively stable hydrology. At the time, the structure stood roughly 340 feet tall, anchoring a reservoir sized to meet mid-century demand. Its storage capacity, about 42,000 acre-feet, was sufficient for decades. The system was not overextended. It operated with reserve. That reserve has since eroded. Population growth along Colorado's Front Range steadily increased baseline demand, while climate variability reduced the reliability of supply. By the late 2010s, Denver Water faced a structural imbalance. Most of its storage sat south of the city, while demand growth was strongest to the north. The Gross Reservoir, positioned in Boulder County, had become strategically important, but its physical limits prevented it from absorbing additional load. The expansion plan addressed that single constraint: height. Raising the dam by more than 100 feet would increase storage capacity to approximately 119,000 acre-feet, nearly tripling the volume available at the same site. In operational terms, this would allow water managers to shift seasonal surpluses forward in time, banking runoff during wet years and drawing it down during prolonged droughts. The reservoir would become a shock absorber rather than a pass-through node. But increasing height fundamentally alters how a dam behaves. A gravity dam resists water pressure primarily through weight. As height increases, the amount of concrete required grows rapidly, along with thermal stresses during curing and long-term material fatigue. Beyond a certain point, mass alone becomes inefficient. That is where arch behavior becomes advantageous. By curving the load into the surrounding rock, an arch dam reduces the amount of material needed while increasing structural efficiency. The gross dam expansion effectively merges these two approaches. The original gravity section remains in place, while the raised portion functions as an arch, transferring force laterally into the canyon walls. This hybrid configuration is rare. It demands precise control over geometry, bonding surfaces, and construction sequencing. Old and new concrete cannot behave independently. Differential movement, even at small scales, would accumulate stress over time. To manage this, engineers selected roller-compacted concrete for the new section. Unlike conventional concrete placed in large blocks, this material is delivered in thin layers, spread and compacted mechanically. The method reduces curing temperatures and accelerates placement, allowing hundreds of thousands of cubic yards to be added efficiently while minimizing internal cracking. By the midpoint of construction, the expanded structure had reached the elevation of the original crest. From a purely physical standpoint, the dam now possessed the capacity it was designed to achieve. The spillway, control structures, and downstream steps were being completed in sequence. The system, structurally, was converging toward its final state. Legally, it was not. Federal permits governing the project focused on construction impacts, not operational outcomes. Environmental review documents assessed how the dam would be built, but stopped short of fully accounting for how the additional storage would affect downstream river systems over time. That omission mattered. As scrutiny increased, the project encountered a constraint no amount of concrete could resolve. The dam could be raised. The reservoir behind it could not yet be used. That mismatch between physical capability and institutional authorization would soon dominate the project's trajectory. The moment construction reached full height, the project entered its most unstable phase. Not structurally, but institutionally. From an engineering perspective, the dam had crossed its most difficult threshold. From a regulatory perspective, it had not. The original approval process treated the expansion as a modification of an existing asset, not the creation of a new one. That distinction mattered. Environmental assessments focused on construction noise, material transport, and local disturbance. They did not fully model the downstream consequences of holding an additional tens of thousands of acre-feet of water within the Colorado River basin. As long as the project remained theoretical, that gap drew limited attention. Once concrete began stacking upward, it became unavoidable. Opposition consolidated around that omission. Environmental groups argued that increasing storage at Gross Reservoir would change how water was extracted from an already stressed system. The Colorado River's average flow has declined by roughly 20% compared to 20th century norms. Every new storage decision now competes against shrinking supply. In that context, adding capacity is not neutral. It shifts risk downstream, redistributes scarcity, and locks future operating behavior into place. Legal challenges followed. In federal court, plaintiffs did not argue that the dam was unsafe or poorly built. They argued that the permitting process failed to consider reasonable alternatives and cumulative impacts. Specifically, they challenged whether federal agencies had adequately assessed options such as demand reduction, distributed storage, or operational changes within the existing network. In April 2025, a district court agreed. Construction was halted under injunction. For the project, the timing was critical. By then, much of the new structure was already in place. The stepped downstream face had risen well above the original dam. Roller-compacted concrete had bonded to the older gravity section. Pausing indefinitely introduced a new risk, an incomplete hybrid structure exposed to seasonal hydrology without its final operating configuration. Denver Water argued that leaving the dam unfinished created its own hazard profile. Without completion, the structure could not safely manage extreme inflows. Spillway capacity control systems and downstream protections were designed to work as an integrated whole. Partial completion was not a stable endpoint. Within weeks, the court reversed course. Construction was allowed to resume. That decision resolved only half the problem. While crews could finish the dam, permission to fill the expanded reservoir remained unresolved. Operational authorization requires a separate set of approvals, including revised environmental analysis accounting for long-term water storage and release patterns. Those reviews must address impacts across state lines because the Colorado River system does not stop at county or state boundaries. As a result, the project entered a state of functional limbo. Physically, the dam could soon stand at its full 471-foot height. Financially, costs continued to accrue, with the original $500 million estimate under pressure from legal expenses and extended permitting. Operationally, the additional storage remained hypothetical. This disconnect exposed a deeper systemic issue. Infrastructure projects of this scale are no longer governed by engineering feasibility alone. They are constrained by legal durability. A structure can be sound, complete, and technically capable, yet remain unusable if institutional alignment breaks down. The Gross Dam expansion illustrates that failure mode clearly. The system was designed to increase resilience. Instead, it revealed how modern infrastructure can stall not because it fails, but because its authorization lags behind its construction. By the time the final concrete is placed, the most difficult part of the project may still be unresolved, not in the canyon, but in the regulatory process that determines whether the reservoir can ever operate as intended. The dispute surrounding the Gross Dam expansion is not fundamentally about concrete or construction technique. It is about how water is allocated inside a system that no longer behaves the way it did when most of its infrastructure was designed. The Colorado River Basin was engineered around assumptions of abundance. 20th century compacts divided water based on flow estimates that no longer hold. Storage reservoirs were meant to smooth out seasonal variability, not compensate for long-term decline. As average flows decreased, storage began to function less as a buffer and more as a point of leverage. Whoever controls capacity controls timing, and timing determines who bears shortage first. That is the concern driving opposition to the project. By expanding storage at Gross Reservoir, Denver Water would gain the ability to capture and hold additional runoff from the Colorado River system through trans-mountain diversions. While this does not increase total water supply, it changes how water moves through the network. More water retained upstream means less water passing through downstream reaches during certain periods. In a fully allocated river system, those shifts matter. Critics argue that the environmental review underestimated this redistribution effect. The permitting process evaluated local impacts, tree removal, construction traffic, noise, but treated basin-wide consequences as marginal. That approach reflected older regulatory logic, where incremental changes were assumed to be absorbable. Under current hydrologic conditions, that assumption is no longer safe. The legal challenge forced that issue into the open. In response, Denver Water emphasized mitigation. Commitments were made to release minimum flows into adjacent creeks, restore wetlands, and offset deforestation associated with the expanded reservoir footprint. Approximately 200,000 trees would be removed as part of inundation, with compensatory measures planned elsewhere. From an engineering standpoint, these mitigations are measurable and enforceable. From a systems standpoint, they do not resolve the core tension. Dams do not simply store water. They reorganize river behavior. Flow timing affects temperature, sediment transport, and ecological cues. In stressed systems, small changes compound. Environmental groups opposing the expansion argue that once additional capacity exists, operational pressure will push it toward use, regardless of initial commitments. The concern is not immediate misuse, but long-term path dependence. At the same time, Denver Water's position reflects its own constraints. The utility does not receive general tax funding. Capital projects are financed through ratepayers, connection fees, and ancillary revenue streams, including hydropower generation at the dam site. The expansion was approved at an estimated cost of $531 million, with the expectation that added storage would reduce long-term risk and stabilize supply for a service population exceeding 1.5 million users. From that perspective, failing to complete the project leaves the system exposed. Climate-driven volatility does not pause while legal processes unfold. Storage deficits translate into emergency restrictions, economic disruption, and heightened wildfire and flood risk. The utility's mandate is reliability, not basin-wide reform. This is where the system fractures. Water infrastructure was built to optimize local reliability within a shared river system. Climate stress has turned that optimization into a zero-sum problem. Projects like Gross Dam sit at the fault line between municipal risk management and collective resource governance. Both sides are acting rationally within their own frameworks. Those frameworks no longer align. As the dam approaches completion, the unresolved question is not whether it can hold more water. It is whether the institutional system governing the river can accommodate another major control point without triggering broader instability. That question cannot be answered by engineering calculations alone. As construction nears completion, the Gross Dam expansion enters a phase that engineering schedules rarely account for: waiting. The concrete work can finish on time, the spillway and control structures can be tested, the downstream face can be stabilized and sealed. None of that resolves the central uncertainty, whether the expanded reservoir will ever be allowed to operate at its intended capacity. Filling a reservoir is not an instantaneous act. Under current plans, bringing Gross Reservoir up to its new operating level would take roughly 5 years, assuming permits are granted and hydrologic conditions cooperate. The process must be gradual to manage downstream flows, protect water quality, and avoid destabilizing slopes newly exposed to saturation. That slow ramp-up makes regulatory approval even more consequential. Delays compound over time. The U.S. Army Corps of Engineers, which issued the original permits, now faces the task of revisiting its analysis. The court found that prior environmental reviews failed to adequately consider cumulative and basin-wide impacts. Correcting that record requires new modeling, public comment periods, and interagency coordination. None of those steps move quickly, and each introduces opportunities for further challenge. This places the project in an unusual position. Capital has already been committed, physical risk has already been assumed, yet the operational outcome remains contingent. From a systems perspective, this is an inversion of the typical infrastructure life cycle, where authorization precedes construction and risk follows completion. Here, risk has arrived early, while certainty has been deferred. The financial implications follow the same pattern. The initial cost estimate of just over $500 million did not account for prolonged legal engagement or extended idle periods between construction and operation. While the project is not funded by general taxation, cost overruns ultimately flow back to ratepayers. Each year the reservoir remains underfilled reduces the return on investment the expansion was designed to deliver. There is also a less visible cost, foregone flexibility. Without the additional storage online, Denver Water must continue operating within a narrower margin. That means drawing more heavily on southern reservoirs, increasing reliance on interbasin transfers, and maintaining higher vulnerability to drought-driven restrictions. The system functions, but without the buffer the expansion was meant to provide. None of these outcomes indicate technical failure. The dam performs as designed. Materials behave within specification. Construction methods have delivered the intended structural transformation. What failed to synchronize was governance. The legal system evaluated the project through a different lens, one focused on cumulative impact rather than local necessity. Both evaluations are valid. They were simply not reconciled before irreversible steps were taken. This misalignment exposes a broader challenge facing large-scale infrastructure in the United States. Projects increasingly operate at the intersection of local need and shared systems. Water, in particular, resists compartmentalization. Storage decisions made in one watershed propagate effects across entire basins. Regulatory frameworks built for incremental change struggle when each increment now carries systemic weight. The Gross Dam expansion did not create that reality. It revealed it. By the time the final permits are decided, the structure itself will already stand complete. Whether it functions as a fully integrated part of the water system or remains a constrained asset operating below its design potential depends on decisions made far from the construction site. The outcome will determine not only how this dam is remembered, but how future water infrastructure projects are approached in an era where technical capability and institutional consent no longer move at the same speed. When the Gross Dam expansion is fully built, the physical work will be largely invisible from a distance. The canyon will look much the same as it did before, aside from a higher crest line and a stepped downstream face. From an engineering standpoint, the transformation will be complete. From a systems standpoint, the project's outcome will still be unresolved. If permission to fill the reservoir is granted, the expanded storage will gradually enter operation. Over several years, water levels will rise, operating rules will be tested, and the reservoir will begin absorbing seasonal variability as intended. The system will gain flexibility. Risk will be redistributed across time rather than absorbed all at once during drought or flood events. In that scenario, the expansion will quietly achieve its stated purpose. If approval is delayed or denied, the dam will operate below its design potential. The additional height will remain largely symbolic, structurally present, but functionally constrained. The investment will not fail outright, but its benefits will be deferred or diminished. The system will continue to function, but without the margin the project was meant to restore. Either outcome carries implications beyond this site. The Gross Dam expansion has already altered how future infrastructure projects will be evaluated. It demonstrates that technical feasibility is no longer the dominant threshold. Projects must now survive prolonged legal scrutiny that extends well beyond construction impacts and into long-term system behavior. That scrutiny is not an anomaly. It reflects a reality in which environmental limits, legal durability, and public legitimacy shape infrastructure as much as engineering calculations do. For water utilities, this creates a planning dilemma. Storage projects take decades to conceive, permit, and build. Hydrologic conditions are changing faster than that. Legal frameworks evolve unevenly across jurisdictions. By the time a project reaches completion, the conditions that justified it may have shifted again. Designing for uncertainty becomes as important as designing for capacity. The Gross Dam did not encounter these forces because it was poorly planned. It encountered them because it sits within a system that is reaching its limits. The Colorado River Basin can no longer absorb incremental change without consequence. Each new control point forces a broader reckoning over allocation, timing, and responsibility. In that sense, the project's difficulties are not unique. They are indicative. Large-scale infrastructure is increasingly judged not only on what it delivers locally, but on how it reshapes shared systems. When those systems are stressed, alignment becomes harder to achieve. Delays, reversals, and partial outcomes become more common. The dam itself will endure. Concrete structures of this type are built to last for generations. The question is not whether it will stand, but how it will be allowed to operate. That decision will be made through legal processes, environmental reassessment, and political negotiation rather than engineering analysis. By the time those decisions are finalized, the expansion will already exist as a physical fact. What remains uncertain is whether it will ever function as the stabilizing element it was designed to be, or serve instead as a case study in how modern infrastructure can reach completion before consensus does. In the end, the Gross Dam modernization is not failing because it cannot be built. It is struggling because building is no longer the hardest part. The system around it has changed.